dimensions. And this work has been done in collaboration with my former student, Avram Klein, and with Igor Aleiner from Columbia University. But before that, I want to really thank the organizers for inviting me to give this talk, because I'm an alien in this field. I came from condensed matter, and I guess that it's a true open-mindedness and a true correct spiritual attitude, scientific attitude, to invite me to give a talk, although they don't know at all. And even worse than that, it is probably a problem which is very different from what I was here 1 week, more than 1 week, from what the community is interested in. So to explain why, let's recall what we all know. Let's suppose that we have some system that we understand, let's say an atom. And after we understand it, there are two routes of research. One is to try to understand bigger scale, to try to understand what happens when this atom interact with other atoms, generating molecules or lattices, and to study there. The other way is to go inside the atom and to try to understand its internal structure. You know, the nucleus, magnetic moment of the nucleus, and so on. Now, if I go to superfluids, then essentially everything is happening only in the larger scale. And this is more or less what this conference is about, understanding what happens when you interact, many vortices interact one with the other. And of course, you can generate many, many interesting dynamics, and so on. And there is essentially almost nothing that happens at small structure. And the reason is very simple, because we all believe that Helmholtz theorem applies, and that essentially a vortex is pinned to the flow. So there is no degree of freedom to play with. So what we think is that, okay, vortex is pinned to the flow, there is maybe a core, not core, but it's not so important. Okay, this is what I said. This is just some example, right? I mean, trivial example. There is also this kind of example of motion, but it's not that important. What I'm going to talk about is a situation where actually Helmholtz theorem does not apply. It applies for in the strong coupling regime, as I will explain, but actually in the weak coupling regime, where Gross-Pitaevsky applies, it does not apply. And so I'm going to look at this limit, where I'm going to consider distances which are much smaller than the healing length. Okay, so what is this physics associated with? It's associated with a situation where a vortex actually moves with respect to the flow. It is not pinned to the flow. And what happens in this situation is that there is a non-analytic core reconstruction, as I will explain. So what happens is that suppose that there is a vortex that moves with respect to the flow. So it is now drawn here. What happens is that the core reconstructs by generating a cut. And here is a plot of a cross-section along this line, which shows how this density, or actually square root of the density, behaves. And this is a plot in the vertical line where there is this behavior. So this is this slide is just a very short summary of all the results that I'm going to tell you. Of course, what I would like to say is that although it is happening only on the small scale, the fact that there is another degree of freedom, which is dipole-like, also affects large scales. And for example, we know that vortices generate a kind of triangular lattice, Abrikosov lattice. And what I would like to claim, although I will not be able to, in fact, 45 minutes to explain that, is that these vortices actually change the position in a shear way, and that cuts are open and generate some kind of super vortex structure, as I show here. These cuts which I told you about. So it's not only limited to just small scale, it is important also on large scale. Okay, so I hope that the organizer will not regret inviting me. I have a good joke to take about it, but I will tell it only in question time if somebody will ask me. Okay, so since we are talking about a situation where vortex moves with respect to the flow, let's start just with preliminary considerations and just try to understand the hydrodynamics of this. So I'm going to consider one vortex in the world in 2 dimensions, and I'm going to consider it in distances much, much larger than the Healing length. So hydrodynamics applies. So we know there is velocity field, there is density field, and there are conservation law. There is conservation of mass, there is quantization of vorticity, and there is Bernoulli equation. This is what we have in this case. And if we want to consider a situation where the vortex is at rest with respect to the flow, so it moves with the flow if you want. Of course, I can do always Galilean transformation. Then what happens is the following. To solve this equation, it's easy to use a complex notation, write V as Vx plus I Vy. And then it is trivial to see that this equation is satisfied by I divided by x minus Iy. So this is, again, complex coordinate, or the conjugate coordinate. And then if I will just substitute this equation here, I will get that n is 1 minus v squared over 2. I work with dimensionless units. Density is 1. Healing length is 1, and so on. And at large distances, which is the limit we are interested in, it's essentially 1. And then I can check that this solution goes through this conservation law very easily. What happens if we try to consider a situation where the vortex moves with respect to the flow? So I'm going to consider a situation where the velocity field far from the vortex core is just constant, Vc. Then I can try to solve these two equations, the conservation of particles and the vorticity quantization. And these two equations will just give me n equal 1, and that the velocity is essentially just superposition of the velocity and the velocity generated by the vortex. But this equation does not go through this Bernoulli kind of equation. So if I want to solve it, what I can do is try to use perturbation theory in Vc, in this velocity. So velocity, when I say velocity here in dimensionless units, it's always in dimensions of the speed velocity, speed of sound. And in this case, I assume that Vc is much, much smaller. And then what I can do is just expand in higher power of 1 over z squared. So this is the solution that you get, sorry. This is the solution that you get. You get that there is some additional function here, which is logarithmic in z and constant. And it is divided by z squared. And of course, this constant is what cut off this logarithm. So this d1 is when you put z equal 1. 1 is, again, the core size. It is the healing length. Okay, so you can also do higher order perturbation theory with logarithmic accuracy, and you will see that essentially this velocity looks like Vc times I minus V minus D, Z minus D. And so this is kind of the first expansion of this guy here. And which means that actually, and this is something which I will return to afterwards, that you go away from the vortex and you try to see where it is located, then it is actually shifted by some amount. And we call this the virtual position of the vortex, okay? So now everything is well known. I mean, nothing is new about this. Although I didn't see this perturbation theory, I guess that many of you knows it. It's not a big deal. But the question is, how do we set this constant here? What is this constant, D1? What cuts off the logarithm? So naively, what everybody believed before is that essentially it is constant of order 1 times VC. That's it. But what I want to show you here is that actually it is not that. It is cuts at much smaller scale, not 1, but 1 over VC. So I have 1 over VC in this logarithm with minus sign here. And this is the cutoff, and this is the dipole moment, which I will talk about. Okay? So to explain this result, I want to start with, to do a little bit detour to explain what I'm doing it. And I think it is kind of important because, again, I'm coming from different community. I have different views. Maybe many of them are wrong. It will be nice to hear about them, about it from you. But eventually, we are talking about quantum system. And quantum system, we have to consider integration over all configurations of the fields. So we have to calculate some integral like that. And the action which we have here has some time dependence and some part of the energy. And the energy is this Gross-Pitaevsky action, if you want, or energy gradient of psi square. And here there is lambda, which is the dimensionless coupling constant. You can see that it is dimensionless. And there is psi square minus n0. N0 is the average density. Okay, so this is what we have. In the weak coupling limit, lambda is much, much smaller than 1. Then it is a very nice way to do is just to dimensionalize everything. And I will measure distances in length of the healing length. Healing length in this action is just 1 over square root of lambda n naught. And the t I will measure in this combination, h bar t divided by m psi square. And psi square I will measure in units of n naught. Then what happens is very nice, is that this action transforms to this one. So you can see that here there are no parameters anywhere whatsoever. It is completely parameter free. And what happened is that lambda appears here as 1 over lambda. Namely, lambda plays a role similar to h bar in quantum mechanics. Yes? Lambda is here, I set it to be the interaction constant. So what people, I think in this community, you call it G tilde. Okay? Excuse me? It's dimensionless. You can see that here there is a, 1 over length to the 4, and here there is also 1 over length to the 4. So this is dimensionless. Yes? N naught is dimension. There is dimension to n naught. This one is length, right? Because this is dimensionless. This has 1 over L, so it is dimension of it's 2D, everything is 2D, 0 temperature. Okay, so we have this action with 1 over lambda, and of course, again, in principle, we have to calculate all these field integrals. We have to take fluctuations into account, but if lambda is very, very small, then this prefactor is very large, and it is stabilizing these fluctuations. And then you just say, okay, let's do saddle point approximation. This saddle point approximation will control more or less the behavior of the system, and you will get the Gross-Pitaevsky equation. Right? I'm going to work in this limit, and the question that you all ask is, how can you tell us something new after, I don't know, 70 years or even more of studying this equation? And the point which I want to say is that part of the physics which is missed is the weak solution of the Gross-Vitebsky. What are weak solutions? Weak solutions, you can view them as minima of this action, but they are not solution of the Gross-Vitebsky equation. In other words, it is a situation where the solution is satisfied almost everywhere in space, the Gross-Vitebsky, except for a measure 0 set. In this case, it is a cut, which looks like that. Okay, I know that this is very difficult to grasp, and I know that most of you say, look, I know that I can work with analytic function, I don't know anything, don't need anything more, but I'm suggesting this, and there is a proof for this, and I hope to just give you the gist of it. But let's start from what happened. So essentially what happened is that we started with some numerical calculation, and this numerical calculation gives us this cut. It is different from Gross-Vitebsky. I will explain in a minute how it goes. Yes, sure. I'm not sure that it is exactly the same. No, it's not exactly the same. And I tell you why. Because usually in, let's say, in the Burger's equation or something like that, you add viscosity and you take it to 0, you will get your weak solution. In this case, no, of course not. I'm not trying to say. But in this case, what happened is that, of course, you have a cut, which is a kind of a very awkward thing to have. But there are quantum fluctuations. Quantum fluctuations, of course, erase things. And you have to take them into account. That it's a minimum of the action, but not a solution of the equation of motion. Yes. I will show you how I get this, okay? Okay. I know, integration by parts. Yes. Right, because as you pointed out when we talk about, there are some kind of mathematical proofs that say that you can do it, but it is assumed something about what happened in infinity, and this solution velocity in infinity is finite, and it is not applied. This theorem do not apply. Okay, so sure. This is no, this is not the density, it is square root of the density. Okay? Okay, so these are numerical solutions which we get. We got it long time ago. It took us 2 years to believe that they are correct. This is a solution which you get, analytical solution which you get in small distances. It is kind of a little bit complicated solution. So again, I write it in terms of complex coordinates, and there is this big Z, which is Zhukovsky transform of small z, and then there is this combination, and this line is just this solution, and the dots are just perfect match to the simulation which we got. Yes, absolutely. Okay, so no. No. No, it's not. The vortices, I mean, it moves with respect to the flow. It can have a lot of. I hope that I will answer all these questions. I know that it is kind of difficult to grasp at first time. I mean, for us, it took us 2 years to believe it and half a year to prove it. And I guess that to give you it in 45 minutes is too much. But I will try my best. Okay, so this is another view of the flow around the vortex, which you get, and it just, encircled the cut. And in what sense it is weak solution? if you will, if you will try to compute the phase of your system here, then what you will see that, of course, you accumulate a 2 pi phase here. And, but what happens is that when you go along the cut, there is a jump on this phase. So there is nothing that is problematic physically with that, because density here is 0. But there is a jump. It is depending, the jump depends on the distance from the point vortex. So the point of the vortex is just the point where you encircle and you get 2 pi phase. So this is, in this sense, it is weak solution. And if we look at the small distances, so I'm going to take this solution which I get. I will look at a situation where Z is much smaller than 1. 1 is the healing length, but much larger than VC. Then what I will get immediately is that psi is, has this alpha Z. This is the usual result of a vortex. And then there is some logarithmic dependence. And this logarithm with this 1 over C is this source of the cutoff which I explained at the beginning. Yes? Yes. Yes. This is not measure 0. You have to have something of measure 0. Otherwise, it's not. No. To go to a second Riemann sheet, you mean? Yeah, sure, of course. This is what we did actually to get this solution. Of course. I mean, this is Joukowsky transform. It's just, you know, it's with one cut, right? It's a genus 0, and everything is very clear. Okay, so I'm not going to show you how to prove, because the proof is really long, but I want just to explain the idea of how we prove it. So the idea is the following. What we did is that we know very clearly to do the hydrodynamics on large scale. This is what I showed you at the beginning. We know to get this exact asymptotic solution at small distances. And the point is that we have to match the two, and they do not match at this distance. But then what we can do is the following. We can solve Bogolyubov equations for the intermediate distance, which is correct at distances much larger than VC, and at the order of 1 over VC. What are these Bogolyubov equations? You just, if you want, take Gross-Pitayevsky equation, you insert the solution for a vortex which does not move, and you perturb it with this velocity. And then you add the additional terms, and you get Bogolyubov equation, and you can solve them. And when you solve them, you can just identify what are the solutions, and you can see that all of them match together to get into this. This was the way that we were proving this. Details can be found in our papers. Actually, it's interesting that when we did this calculation, we realized that Taules did it also, and he got this logarithmic solution, but he threw it away as non-physical. But here we see that actually we can trace it back to this core reconstruction. Okay, so what are the basic consequences of this non-analytic core reconstruction? So first, it means that there is not only position and vorticity charge of a vortex. There is also an additional degree of freedom, which is like a dipole moment, this kind of cut. Second, there is some mass to the vortex, and this mass is actually large. It goes like logarithm of 1 over VC. And so it depends non-analytically on the velocity of the particle. So how you can do that? Essentially, it's very simple. You just take our analytical solution. You can insert it into this energy, calculate the energy minus the energy as VC, and you will see that there is a term which goes like m over 2, and this m goes like log 1 over c. So the added mass is large. It can be large. Of course, it's only logarithmic, but it is large. what happens then? So then what I want to claim is that there are some situations where the vortex actually can just experience rotational, it is single vortex, which experience rotational motion. And the reason is because we know that a particle in magnetic field, a vortex is like a particle in magnetic field which experience a Lorentz force. It makes circles. But usually why in the traditional way it is neglected is because the mass is small. If the mass is small, then the frequency is very high. And if the frequency is very high, it is high energy state, which usually relaxes immediately. So we can forget about this. But our claim is that mass is not small. It's actually large. It is logarithmically large. It is large. I have a parameter here. Lambda can be as small as I wish. So if it is small, then I can have a situation where a vortex can just do circles like that. Of course, you can ask whether it is exists for a long time, because when a vortex is doing circles like that, it generated waves, and these waves, it radiate waves, and these waves will dump it. And the question is whether it is long time. And here there is a situation where, we have luck. And the reason we have luck is as it's related to this virtual position. Because these states which I'm talking about actually keep the virtual position of the vortex at distances of order of the Healing length or a little bit larger as actually the same. So what happens is that the coupling to the phonon is extremely small. There is an additional factor of 1 over lambda. So here this is one. So the rate of dissipation, if you want, or relaxation is log over to the power 4 of 1 over lambda. Lambda is the coupling constant. It is much smaller than the energy, if you want. I didn't say what is the energy, but I can calculate by quantization the energies of this system by just Bohr-Sommerfeld quantization, because the relaxation resonances are well defined. And then there is a series of peaks. So there are a series of energy states which the vortex can be. This is already quantum mechanics. It's not on the level of just Gross-Pitaevsky, it's above this. I mean, taking fluctuations into account. This is a good question. Okay, so let's say, just one moment. Let me tell you something. Just let me tell you something. I mean, of course, in the strong coupling regime, like helium, you will not see anything. Yeah, because you can see lambda is of order 1, then there is nothing. But if we are talking about BEC, then let's ask what is this lambda. And it turns out that in all the experiments which I saw, lambda is of order of 0.1. It's not enough. You can see that it is not enough. Okay, so when I estimated what's going on here, then I saw that I need something of order of at least 2 orders of magnitude smaller to really see something in experiment. So 0.0.01. 0.001, which is not, which actually I think it should be accessible, but all the experiments I talked to, they claim that it is difficult to do. I mean, it depends what is the size of the system, right? Depends what's the size of the system. But okay, of course, there are some other possibilities. I mean, you can look at, for example, superconductivity. Superconductivity, there is also something which is, delta satisfies something similar to Gross-Pitaevsky. And you can try to look there. There, the healing length can be very large if you are in the right conditions. Again, when I try to talk about experiment, it is not easy to do. because there is also disorder. Okay, so how we did. So everything I told you is just the gist of the result. I want to tell you what is the way that we derive this. And I think that it is important for you to understand my approach for this, because I all the time hear from you, there is nothing else but Gross-Pitayevsky equation. But I want to say that there is something else, and it is Popov equations. Now, Popov wrote a book about it, but if you would like to see the equation which I'm going to present, you will need very creative reading of it. You will not see them there. So what we do is go along the following way. So, but the idea is Popov. We don't try to take any credit for that. So we start again from this field integral with this action, and we do the Madelung transform. There is nothing to say. You all know this. I'm going to work in coordinates where time is x0 and space is x1 and x2. And then there is velocities. Again, velocity 0 is time derivative of the phase, and the velocity x and y is the x derivative and y derivative of the phase. Okay, so the problem with this, as you all know, is that it is very awkward to work with the phases, because each vortex is actually a branch point where this branch point of a cut where there is a jump of this phase, and where when you have many vortices, you have many branch cuts, you cannot do anything essentially. So Popov's idea is the following: let's treat these velocities as independent fields instead of this phase. What you have to pay is you have to constrain it by this constraint about the vortex density current and the relation to the velocity field. Epsilon ijk is just the Levi-Civita tensor, the antisymmetric tensor, and the vortex density is here, J0 is just the position of the vortices. Sigma is the vorticity charge, and the vortex velocity is again something like that, but multiplied by the velocity of the vortex. R is the position of the vortices. Okay, so then what you do is the following. You say, let's put this constraint with Lagrange multipliers. So Lagrange multipliers I have 3 because it is a vector equation, A0, AX, and AY. But now you can see that this action actually is quadratic in V, and I can integrate over V. So I integrate over V, and I get Popov action. This is Popov action. And what is written here? So there is E, which stands for the electric field. There is B, which stands for the magnetic field. It's 2 dimensions, so B is a scalar in 2 dimensions. And B is related to this vector potential according to the usual electrodynamic equation you know. It's rotor of A, and E is, again, there is a scalar contribution, and there is derivative of the vector potential. Okay, so what we have here is essentially nonlinear electrodynamics, which is coupled to vortices which are like charge. It is nonlinear because you can see that B appears in the denominator here. And this is actually dictated by the fact that we have to have an action which is Galilean invariant. Now, what Popov did is essentially he erased this B in the denominator, and then he gets something which is Lorentz invariant, which applies at very large distances. But we want to see what happens on the level of a core, so we cannot do that, and we have to keep all of this. This is exact. There is no any approximation here. Yes? Okay, so next we can do the equations of motion. So for example, from these relations which I told you that exist from here, then you will get that from this B and E, you will get just Faraday wave, which is nothing if you trace it back to the original variables, it's nothing but the continuity equation. If you take the derivative with respect to the scalar potential, you will get Gauss law, which is essentially the vortex quantization, vorticity quantization. Take the equation with respect to the vector potential, you will get something which is the correct form of Bernoulli, of Bernoulli equation, if you want, which applies everything on every distance. So this is just Ampere-Maxwell law. Here, when I write epsilon, it is the antisymmetric tensor in 2 dimensions. So there is kind of, it rotates by 90 degrees. And finally, I can take derivative with respect to the position of the vortex. And what I will get is just the Lorentz force, as expected. So it's Magnus force or Lorentz force, which is expected to get. Okay, so we have essentially here nonlinear electrodynamics of charged particles and fields, which are coupled together in the usual way. Okay? Just to summarize this analogy, so we have charged particles which are like vortices. We have the position of them, which is the same in both pictures. Charge in the electrodynamics is vorticity charge in the superfluid part. The electric field, which is rotated by 90 degrees, is just the supercurrent. The magnetic field is the superfluid density, and Lorentz force is Magnus force. So example for this, the usual vortex, we know that the superfluid rotates around this vortex in this form, but the relation is that n is like b, as I said, jx is like ey because it is rotated. The magnetic field, the electric field is rotated by 90 degrees with respect to j, and j, I mean, it should be jy, is minus ex. So in this picture, this vortex, which is a charged particle, is just generating the usual electric field which we expect, radial field. Okay? So why this approach works? This approach works because the weak solution of the Gross-Pitayevsky are essentially strong solution of the Popov equations. So when we solve Popov equations numerically or exactly or whatever, then these solutions there is nothing special about them. They are not a weird solution. They just come out naturally from the equations. A weak solution, as I said, weak solution is solution which is minimum of the action, but not necessarily or not a solution of the saddle point equations. Strong solution is a solution which is a solution of the equations themselves. So this, I wrote you this set of equations here, right? I have several equations that I have here. So when you solve them, then it is just solution which is have this property which I showed you before. I mean this. Yes, of Popov action. Yes. I don't need at all. On the contrary, I shouldn't have Lorentz invariance. I have just Galilean invariance. If it is Lorentz invariance, I cannot say anything about this. Okay. So just some. I want to. I'm not. How much time do I have? Is it 10 minutes? Okay. It's not a lot, but I just want to mention some of the consequences of this additional degree of freedom. So one of them is the following: is that if you take just two vortex-anti-vortex, we know that in the usual picture, the only solution you have is that they just move together. Here we find that there is a lot of set of new solutions, which they can generate some motion like that or some motion like that, and so on. If you have two vortices of the same sign, they can generate also motion like that. It's not that we don't have the original solution. We do have them, but also additional solutions, because there is additional degree of freedom. Another example which we considered is a drag of vortices. So we take, so there are two possibilities to try to make this experiment. Nobody did it yet. One is to try to take C and instead of moving the vortices themselves, taking a disordered potential and move it through your condensate. And you can do it by this disordered potential. People do it by moving a speckle pattern through the speckle pattern, which is generated by laser through the system, and you can get something which looks like disordered potential that moves in the system. Another situation is that to take a very thin films of helium, and of course it is on a substrate. There is always disorder there. If the film is sufficiently small, thin, then the interactions become small, and you will reach to, in principle, to the weak coupling limit. Although when I talked to one of, I think, the best experimentalists in the past about this, Bill Gleberzon, he told me that to get to lambda much smaller than 0.1 is extremely difficult and probably impossible. But on the level of theory, I can fantasize. So what happened in this case? So suppose you have, you just put a flow and you have vortices there, and so you rotate the system such that there is these vortices inside. So, and then there is a flow. So to the first approximation, what happens is that flow just drags the vortices with it. But since there is disorder, then from time to time it will kick a vortex. And it will transfer it to some higher energy state. Now, as I hope you remember, the relaxation time is extremely small. So what can happen in this situation is that you can get hot vortices. So they are at very high energies, while the system itself is quite cold. And in this case, if you calculate the drag coefficient, so what is the velocity of the vortices, let's say perpendicular to the direction, when there is velocity of the superfluid V, there are drag coefficient chi perpendicular and similar to the parallel, and you have a very, very nonlinear behavior of these drag coefficients. And it is because of this heating of vortices, because you are going to exploit these additional degrees of freedom. So additional thing that happen is that actually, if you look at V perpendicular as function of the V of the superfluid velocity, then there is this shape which has 3 solutions for some V perpendicular, which means that there is filament instability. Larkin and Ovchinnikov saw something similar in superfluid, in superconductivity, vortices of superconductivity, and we believe that this is maybe possible to see also here. But it's very difficult to make this system. Another example is what I showed you before, is this Abrikosov lattice instability. So what happened here is that we know that if there is an additional degree of freedom, there are some cases where it's better to exploit this additional degree of freedom and to lower the energy. And this is exactly what happened here. And maybe I will just say something about this. So what I'm trying to say is the following. Suppose we take one vortex, just one vortex. Then we know that without this degree of freedom, which I'm talking about, then there is just one solution where the vortex, the minimum energy of the vortex is just in the middle of your bucket that is rotating. But what we find is that actually it's better, you can lower the energy by just shifting the vortex a little bit. It is pinned, it is stationary. There is a flow over this vortex because it is rotating. But you can get lower energy in this situation. And of course, there is a large degeneracy, a huge degeneracy, because you can shift it in any direction. So if I go to a situation where I have vortex lattice, Each one of them is, is in the position where there is zero velocity from all the other vortices. So I can shift it a little bit and get lower energy. So there is huge degeneracy. And when you solve this and you take the coupling of these dipole moments together, then you see this picture which I showed you before. So there is kind of all these vortices move in a shear wave, and they are opening cuts in some kind of super vortex structure. There is a lot of very beautiful mathematics of Weierstrass function and the Kittel domains and so on that is hidden in this, and I don't have time to tell you about this. And I guess that I also don't have time to tell you about many other things that I wanted to tell you, so I will go probably to the conclusion. Okay, maybe before the conclusion. I think why it's interesting, I think this is, to my knowledge, the first example where we have a weak solution in quantum field theory. And I think there are some other problems which I know that there is possibility to have weak solution also there. One of them is when we look at, it's in high energy, when we looked at multiple magnetic charge, monopoles of multiple magnetic charge, then we know that there is no solutions there. And we talked to Polyakov about it, and apparently there is a claim that maybe eventually there is some weak solution that can explain this. There are other cases, for example, in elasticity, where there are weak solutions. I don't want to discuss it, so I will just thank you for listening. Thank you.